Hi, and welcome to this video on alkanes. Alkanes are saturated hydrocarbons. This means they are made of just carbon and hydrogen and that there are no double or triple carbon-carbon bonds. To better understand this, let's build N-butane, a 4-carbon straight-chain alkane. First, we put our carbons in a row and connect them with a single bond. This is our carbon backbone. Carbon atoms have 4 electrons in the valence shell and as such make 4 bonds to satisfy the octet rule. In alkanes, any non-carbon bond will be to a hydrogen, which is referred to as saturating a carbon with hydrogen. For our example of butane, the 2 terminal carbons will be bonded to 3 hydrogens and the 2 interior carbons will be bonded to 2 hydrogens. This gives us the final structure and the chemical formula C4H10. All straight-chain and branched alkanes have the general chemical formula CnH2n plus 2. In the case of butane, N equals 4, so there are 4 carbons, and 2 times 4 plus 2 equals 10 hydrogens. While this depiction of butane is chemically informative, it's pretty cumbersome to write out every time, so chemists use a shorthand form that just shows the carbon backbone. This zigzag represents butane. Carbon atoms are at each point and each line represents a carbon-carbon single bond. The hydrogens have been removed and we simply assume their presence. These simplified drawings are highly preferred in organic chemistry, so it's helpful to get comfortable with them early. The carbons in alkanes are bonded to 4 constituents, which means they are sp3 hybridized. sp3 hybridized means that the 2 s orbitals and the 3 2p orbitals of the carbon atom have combined to make 4 equal sp3 orbitals. These orbitals overlap with the sp3 orbitals of other carbons or the 1s orbitals of the hydrogen to make sigma bonds, which are the strongest covalent bonds. The 4 bonds are spaced equally around the carbon, which yields a tetrahedral geometry. This means that the carbon backbone zigzags just as the line drawing represented. The main takeaway from all this is that in alkanes, every carbon has 4 strong sigma bonds. This will be important later when we talk about the properties of alkanes. Along with simple straight-chain alkanes like butane, alkanes can also be branched. For example, isobutane, an isomer of butane, is also an alkane as it follows the CnH2n plus 2 formula. Strictly speaking, cyclic carbon frames saturated with hydrogen, for example cyclohexane, are not considered alkanes because they do not follow the chemical formula CnH2n plus 2. 2 of the hydrogens have been replaced by the carbon-carbon bond that closes the ring. However, it's not uncommon to see cyclical compounds referred to as alkanes in less formal settings. Now that we're familiar with the structure of alkanes, let's look at their properties. Alkanes are nonpolar and thus insoluble in water. They are also fairly unreactive. This is for a few reasons. First, because alkanes are nonpolar, there are no areas of partial charge. This means that they do not strongly attract other molecules with partial charge, which is often how reactions start. Second, to form new bonds, the strong sigma bonds we described earlier would have to be broken. While this isn't impossible, it's not the easiest chemistry and it's usually hard to control. That being said, as carbons are highly unoxidized, they are perfect for oxidation-reduction reactions and are commonly used as combustion fuels. Think of propane, a 3-carbon straight-chain alkane in your gas grill. Even though most alkanes are relatively uncommon in nature, it is helpful for chemists and biologists to study their structures and properties. Take, for example, butanoic acid, a compound found in animal fat, plant oils, cow's milk, and breast milk. While it isn't an alkane, you can easily see the underlying 4-carbon alkane within it. In fact, you'll notice the name of the alkane, butane, is the root word for butanoic acid. Vitamin E and open-chain glucose are more complex molecules, but you can still see the underlying carbon frames in both. A useful analogy is to think of the carbon frame as the trunk and branches of the tree, and the functional groups as the leaves and fruit hanging from the tree. Let's finish with a review. We first defined alkanes as a saturated hydrocarbon with the general chemical formula of CnH2n plus 2. We built N-butane, a simple 4-carbon alkane, and learned the shorthand method for drawing alkanes. We then considered the sp3 hybridization of the carbon atoms, connecting this both to the structure and inertness of alkanes. Finally, we looked at a few examples to demonstrate how alkanes provide the carbon framework for many organic compounds. Thanks for watching, and happy studying!